Okay, let's go through the Resit paper for 2022. Okay. Question 1. Question 1A was this. Let's take a look through this. Let me save this so it doesn't get annihilated. Okay. Write the missing pseudocode in the code below of an efficient recursive method to print in order all the values of a binary search tree of integers that fall within the inclusive range from min to max. How could we go about doing this? Right, so we've got this solution from Ilya. Void print range. Okay, so we take in the node, we take in the min and the max, so that's just the method header here. If the tree is not empty, so t dot is empty tells us if it's empty, and this just means not. So if the tree is not empty, then we want to run this. So we want to check if the tree dot value is greater than the min and less than or equal to the max. If it is, then we print the range of t dot left, and we print the range of t dot right, and we print the value in t. And then we return. Is this what we want to do? So let's also paste in all these. Right, yeah, it's a void return. Okay. Yeah, no, that makes sense actually. Here we've got if t is null, return. If t dot val is greater than or equal to the min, then we want to print the range of t dot left. Because we know that this is greater than the min, so everything here is also going to be greater than the min. And then we print this value, and then if this is less than the max, then we know that the max is going to be somewhere on this side, so we also want to print all of the stuff on the right. Cool. I believe both of these would work. The way I approached it was doing something like this. So I did type it out, but yeah. So if the t dot left is not equal to none, then we print range. So I just went through every single node. I guess this would probably be more efficient. But yeah, mine's just essentially a DFS. Yeah, mine's a DFS, I believe. And I think, yeah, Phoebe's got something similar to mine. Wait, why is yours inconsistent? This is Phoebe's solution. If min is less than the t dot val, it's less than max. A bit of t left. Oh right, yeah. But yeah, this would also work. Okay, I'll just paste all of these solutions so I can label them afterwards. I'll just label these two here for now because I'll get confused later on. They're very similar. Oh, what is that font? Ew. Ew. Yeah, so if you had something like 10 and we passed in a min of 12 and a max of 14, and then we had something like 15, this wouldn't print the 15 because at this point we'd just terminate the algorithm. So we just wouldn't go into the if statement, we'd just terminate. So it's not actually checking it exhaustively. It's just saying, okay, we've seen a 10, that's less than the minimum, so at this point we're going to terminate, we're not even going to look at the right or the left side. So yeah, I don't think that top one would work due to that. Yeah. Okay, let's move on to the next part of the question. Okay, the standard algorithm for deleting a node from a binary search tree can be described as follows. Find the node containing the value to be deleted. If it's a leaf, just remove it. Else, if only one of its children is not empty, so if it's something like this or something like this, and the node we want to delete is this one, then we're going to go to this case where we replace the node with the root of the non-empty subtree. So we'd replace this with this, or we'd replace this with this. Else, find the leftmost node in the right subtree, replace the value to be deleted with that of the leftmost node, and replace the leftmost node with its right child. Explain in detail why the complexity of this operation is over log n if the tree is balanced. How did we approach this one, guys? So yeah, the general gist is if it's a leaf, remove it. This is just going to be O of 1. This is just going to be constant. If one of its children is not empty, we replace the node with the root of the non-empty subtree. This is also going to be O of 1. But before we do that, this part's going to be O of log n, because we have to actually find the node. And then, in this case, we have to traverse at most down the entire height, so this is going to be O of log n. So overall, we're just adding these complexities together. Log n plus 1 plus 1 plus log n. And so, when we do O of 1 plus O of 1 plus O of log n plus O of log n, we're just left with O of log n. So that's why, and the reason why this first one's O of log n is because we assume the tree is balanced, and again here we're assuming the tree is balanced. We're using that assumption. Cool. Right, question 2a. Assume an external record file where each record can contain up to 3 records is stored on secondary storage as follows, with record block pointers as indicated and records shown as n star to represent that we're storing some record along with this key value. So this is our record file. We want to construct a secondary index B plus tree on this record file and present our results as a single diagram showing all the secondary storage pointers, blocks, and block contents for all of the B plus tree and record file blocks. Assume that the B plus tree block can hold a maximum of 3 key values. So this is what Ollie's got. So we have our root node. Everything less than 24 is here. Everything greater than or equal to 24 and less than 33 is here. And then everything greater than or equal to 33 is in here. And then, as we saw, we have a node and a key. I mean, we have a key and a disk address. Key and disk address. Key and disk address. So the disk address for 14 is just pointing to this block. Same for 16 pointing to this block. 21 pointing to this block. And then the idea is we just search through this block to find whatever record we want. Okay. Yeah, cool. So this is the correct tree to my understanding. And how we'd construct this, I'll just quickly go through it. So we have our record file. This is our record file. So the first thing we want to do is we want to insert all of these into leaf nodes sequentially. So first we want to order them. So we get 14, 16, 21, 24, 28, 32, 35, no, 33, 35, 42. That looks right. Okay, so we have the ordered keys, and then we just insert it like as if we're bulk loading it. So 14, and then 16, and then 21. So these all go in a leaf node. As soon as we try and insert another one, we have to make another leaf node. So we'd make another leaf node, and here we'd have 24, 28, 32. Because we've got 2, now we need a root for them, so this will look something like this. One thing to remember is that I've forgotten, the leaf levels will also have these, because we can go left and right. I'll do this in a different colour actually. Yeah, leaf level will also have these. I think Ollie's got those in. Oh, yeah, we've got them in. Okay, so we don't actually need it on the left. Yeah, that's a good point. Oh, that's so nice. No more one note rubbing out. Okay. So we'd have one there. We'd have one there. We'd have this one here. We'd have one here. Okay. So we'd post this 24 upwards. But remember, because it's a secondary tree, we cannot get rid of this, because this is going to be pointing to some record in our record file. Yeah. So this 14 is going to be pointing down to, if we just grab our file and bring it down here, this 14 is going to be pointing to here, this 16 is going to be pointing to here, and this 21 is going to be pointing to here. We're going to have this 2A doubly linked list, then this 24, 28, 32, and we've still got some more to insert, so I believe we have 3 more to insert. So we've just inserted 32, we need to insert 33, 35 and 42. So 33, 35, 42. We're going to post this 33 up, but again, remember, we cannot get rid of the 33 from here because it's in a leaf node. So this is going to point here, this is going to point here, and this is going to point here. And then we're going to have these pointers as well. This is going to be a doubly linked list pointer. 33 points here, 35 points here, and 42 points here. So this is what we'd end up with. Hopefully that makes sense to everyone. If not, again, this is being recorded, so should be able to watch that back. If there's any questions, then let me know. Right, question 2b. Assume you have a list of records, each with two fields, x, y, where x is an integer field, and y is a character field. So this first one's an integer, the second one's a character. Explain, showing intermediate steps, how bin sort sorts this list so that it results in all the records sorted by the x field first, and then the y field for groups of records with the same x value. Use the following list of records in the given order for your demonstration. Draw the contents of queues as lists with the head of the list to the left. Okay, so how would we go about this? Okay, I see we've sent some solutions in chat. Let's take a look at these. Yeah, so the idea is we first want to sort by the x value, which is the integer value. So first we group them into the integers. So all of these are 1, all of these are 2, all of these are 3. And we do that via a bin sort. We just go through all of them and we make them all go into separate bins. I'd probably go with Ollie's method of writing it out explicitly just so that we can show the exact steps we're taking when we split it up. But yeah, so we sort by the x values, and then we concatenate those bins into a larger queue of all of it. Yeah. No, we've sorted by... yeah. Right, no, I think this is wrong. So what we'd actually do is we'd... Yeah, because we want to sort it by the x values first. So what we're trying to get to is something like 1A, 2A, 3A. Sorry, no. We're trying to get to something like 1A, 1B, 1C, 2A, all the way up to 3C. Because this is sorted by the x value first, and then the y value. Okay, let's paste in this solution. Okay, so yeah, first because we want to sort it by the x value first, we'd perform the bin sort on the y values first. So bin sort on the y value into 3 bins, A, B, C, assuming y is in sigma. Why are we bringing sigma into this? Okay, I mean, that works. So we have our 3 bins, and we're just grouping it by this y value. So all of the A ones go in here, all of the B ones go in here, and all of the C ones go in here. And then we concatenate those bins into this list here. And then we want to sort on the x values, but using these y values to... like 2 things with the same y value should remain in the same order, I believe. So, right, yeah. So if we split this list into 3 bins now, but now we're using our x values to decide which bins they go into. So this is going to go into bin 3, this is going to go into bin 1, this is going to go into bin 2, and we're going to do this, and we're going to result in this. So after splitting it into bins based on the y value, and then concatenating, we get this. And then splitting it based on the x value and concatenating, we get this. And this is the reason we did it in that order is because we're sorting it by the x value first, and then if things have the same x value, then we're sorting it by the y value. So you can imagine it as something like if we have a date, so 10/05, 11/05, 13/05. Or we're going to use American dates just for this example. So 5/11, so this is 11th of May, 6/11, 6/02, 3/03. Okay, say we want to sort this in ascending order. So the first one is going to be March the 3rd. So if we sorted it by the day first, we'd get something like 05/11, or yeah, we'd get 05/11, 06/11. So this would be in one of the bins. Then we'd have 06/02. This would be before 06/02, and we'd have 03/03. So these would be our 3 bins. And if we concatenated them, we'd get something like this, which is just this whole list. And then if we then bin sorted that based on the month, we'd get 06/02, or sorry, yeah, 06/02, and then in another bin we'd have 03/03, and then in another bin we'd have 0511, and then in another bin we'd have 0611. Sorry, no, that would be in the same bin as this. So the idea is we've sorted it in ascending date order by first sorting it by the least significant and then sorting it by the month. So in the same way here, we're sorting it by the y value first, and then we're sorting it by the x, because we want it to be sorted by the x values, and then we want to sort it by the y values if two things have the same x value. Hopefully that makes sense. Question 3. Draw a diagram of the result of inserting the value 55 into this binomial heap, where the highest priority is the highest integer value, and explain the steps by which you came to your result. So highest integer value, this means we're doing a max heap. Yeah. Okay. So we've got a solution in. Nice and speedy. Okay. So we have our heap 1, and we have our heap 2, which is just other heap. So that's this chunky heap up here. And so first we compare the order 0 trees in both heaps. Because they both have order 0 trees, we're going to merge them into some carry out. And we're not going to have any order 0 tree. Okay, so we have a carry out tree. So this is our carry in for when we're looking at the order 1 trees between those two. So we look at this order 1, we look at this order 1. We don't have anything here, so we just have two order 1s. This is just going to make an order 2 tree. And we don't have any output here. Okay, so this is going to be the carry in for the order 2 tree. So we don't have any order 2 tree in the first heap. We have an order 2 tree in the second heap, and we have an order 2 tree from the carry-in. We merge these two into an order 3 tree, and we don't have any output again because we just merged two order 2s into an order 3, and we don't have any order 2s left. This goes up to here. Oh, I like that. I like that cut off. So we have 3. We don't have any order 3 tree in heap 1. We don't have any order 3 tree in heap 2. So we just have our carry-in, and we don't have any carry-out, and our output is just this carry-in. And so overall, our resulting heap of the merged result of the two heaps is just going to be a single heap where we have no order 0 tree, no order 1 tree, no order 2 tree, and just a single order 3 tree, which we've drawn out here. So this is our final binomial heap. And at every stage we always merged the one that had a larger root. We made the one with the smaller root the child of the one with the larger root. That's just something to keep note of. Okay, and to describe the steps taken, we calculated the order of the new resulting binomial heap by calculating the size/shape. So if there's 8 nodes, 2 to the power of 3, that's an order 3 tree. We merged the binomial heap, including just the binomial heap tree of order 0, containing 55, with the other binomial heap. Yeah, so we made a new binomial heap, which was just an order 0 binomial heap, with the single value we wanted to insert, which was 55. Continuously added binomial heap trees of the same order until there were no more carryouts, and obtained a binary heap tree of order 3. And we added this binary heap tree to a new binary heap, and our merged binary heap, which is this here. Awesome. That looks correct to me. Are there any questions about that question? Okay, question 3b. So consider the following graph. Demonstrate the execution of Dijkstra's algorithm for finding the minimal path on this graph from node A to node C by writing out a table of the execution steps in the following format, where the first row following initialization is already provided. Each row should show the results of one iteration of the algorithm, where the finished column identifies the node that's finished in that iteration, and the remaining columns show the current shortest distance of the node of that column from node A, the previous node, to the node of this column on the current shortest path from A, and a tick mark if the node of the column is finished. Finally, explain how the shortest path and its length can be derived or read from the final line of the table on completion of the algorithm. Yeah. Okay, so in terms of my solution, and I think that's also what Ollie got. Yeah. Cool. So I did just not write in all of the cells, but in the exam, to be on the safe side, I would probably write in all of the cells. So I'll also paste in Ollie's solution table. I'll just, yeah. Okay, so the idea is we want to write in, our initial row is just what they gave us. And at this point, would it be A that was finished in this first row? Because I'd argue that we finish A only after we've updated the distances for A. But I guess we could, I guess we could mark the node as finished before we actually look at the distances. But then, yeah, it's a small difference. But yeah, so the idea is we look at the first row, and then we look at A. So we look at all of A's neighbours. I'm going to paste this graph down here as well. So the idea is, yeah, we look at A's neighbours. From A, we can get to D with a cost of 1, and we can get to B with a cost of 3. So we set the distance to B to 3 and the prev to A, and the distance to D to 1 and the prev to A. C and E we can't get to from A, so we don't consider those two. And we mark A as finished. Then we look at the next node with the smallest distance. So in this case, that's going to be D with this 1, because 1 is less than 3. That's unvisited, so that's why we don't look at A in this case. So we look at D. From D, we can get to B with a cost of 1 plus 1. So B total cost of 2. 2 improves the current 3 we have stored. So we update that with a cost of 2 and the previous node to D. And from D, we can also get to C and we can get to E. C with a cost of 5 plus 1, so 6. So we update that. And we can get to E with a cost of 3 plus 1, so 4. So we also update that. And then we mark D as completed. So we've completed A, we've completed D. Then we look at the next node with the smallest distance. In this case, it's going to be B, 2. From B, we can get to C with a cost of 9. That does not improve our current solution, because we can already get there with a cost of 6. So we don't want to get there with a cost of 9. We can get to... Yeah, so we can get to D with a cost of 4, or... Yeah, with a cost of 4, but that doesn't improve our solution. And we can get to A with a cost of 3, that doesn't improve our solution. We can mark B as finished. Okay. Then we look at the next node with the smallest distance. In this case, it's going to be E, because we've only got C and E that are unvisited. So mark E as visited. From E, we can get to C with a cost of 4 plus 1, which is 5. That improves our 6 that we have already. So we update the distance to C to 5, and we update the previous node to E. And then we can also get to D. That doesn't improve our solution. So that's all of E checked. And finally, C is the last unvisited node with the shortest distance, or the smallest distance. 5. This doesn't improve, this doesn't improve, and this doesn't improve. We mark C as visited, and this is the last row in our table. And then finally, to get the distance to get from A to C, we look at the distance value in that corresponding column. In this case, it's just 5. And in order to... Oh, sorry, wait, was it A to... Finally explain. Oh, A to C, right, yeah. So we can look at the distance, and so it's 5. That tells us it's a total cost of 5 to get to C. And so the node we use to get to C is E. And to get to E, we come from D. To get to D, we come from A, and A is our initial node. So we can backtrack in this last row to find out what our initial route is, starting from our destination and working backwards to our initial node.